My name is Juho Pirskanen. I come from Wirepass. I am the program coordinator of this Celtic project. Before going to the actual agenda and the presentations, few words. So we will record this presentation. So the intention is that the video will become available for the parties that at least who have registered but potentially haven't been able to join now to this session. We have a quite tight schedule, quite many presentations. So please ask your questions to the chat during the presentations, and we will try to consider that can we answer those questions during the or after the presentation, or then we try to figure out the response offline to your question. But as the schedule is tight, we don't have possibilities to have a lengthy discussions and at this time. Mika, would you start the recording now? I think
I already started from the start. Yes.
Okay. So the recording is on. So first few words about the project USWA, Ultra Scalable Wireless Access. So basically, the project has been started in December 22, and it will continue until November 25 or end of November 25. And it is now we are approaching half point of the project, not quite yet, but becoming closer to that. So we thought that it would be good to present a little bit the early findings of the project. There's a lot of work to do still, but the work is ongoing. The project is a Celtic Next project, so it is funded by different national funding institutes. We have participation from Finland, several partners there. You can see all the names of the partners in the slide. Then we have partners from Germany, Spain, Austria, and Turkey. So we have a wide variety of companies and research organizations participating to research on Tech 2020 new radio technology and different applications on top of the mesh communication. The basic project is running as in this figure explains. So we have studies on system architecture and application requirements and use cases, which you will hear also the presentation on today. Then we have two work packages which are studying slightly different aspects of the mesh networking. So the first aspect is the IoT mesh networking on a massive deployments of IoT devices. And then the second research work package is the ultra reliable and low latency mesh network communication, and studying the requirements and solutions for that in different use cases. And then we are doing also different proof of concept implementations for energy networks controlling and monitoring, industrial condition monitoring, industrial IoT and URLC, and simulations and implementations. And of course, when considering the project that we are halfway, we are about to start on these exercises. We are not yet there. We are more on the level that we are studying the use cases, requirements, and technical solutions for that. And then, of course, we have standardization and market analysis and exploitations. So project members are active in Etsy. They are doing market analysis and understanding how different things could be utilized in the real deployments and making business sense in the business wise. So today's presentations are here. So this is my part. Welcome and introduction. Then Ivan Preten from PhoneLabs will take a presentation on USWA use cases and from the requirement perspective. After that, we have Ali Kalifi from ACD Turkey presenting challenges of wireless solutions in industrial environments. Then Jukka Talvitie from Tampere University will present on positioning aspects on EdgeDect new radio. Then my colleague Mirza Alam will present EdgeDect 2020 new radio for MFTC communications research results. And then Andreas Forzer and Julian Weihe, Andreas from Fraunhofer ISS and Julian from NXP will present mesh networking for ultra-reliable low latency communications. And then finally, my colleague Jari Hämäläinen will present the DEC 2020 technologies for proof of concept and product implementation. So giving the, let's say, latest news on that area. And then the target is that we are closing around noon Central European time, so 1 o'clock Finnish time. This is the agenda. Hopefully you enjoy on the presentations and you find it interesting. And with these words, I give the floor to Ivan for the first presentation. Thank you. Floor is yours, Ivan.
Okay. Thank you, Juho. Thank you all for being here. So let me share my screen to start with my presentation. Okay. So as Juho said, I'm Ivan Pretel. I am a research and innovation projects manager in Phone Labs. It's an agile content company, and I am going to talk about the USWA use cases, but from the requirements perspective. I will introduce the topic a little bit and the main pillars we use to gather the requirements themselves. After that, I will describe the use cases and the key requirements. Finally, one summary and a brief conclusions of the work done. So here is one figure to explain that to gather the main requirements, we have based this in two main pillars. Top-down approach on one hand and the use case-centric definition on the other hand. The top-down approach is based on one need, which is that we need to focus on a more realistic requirements, taking the user needs and avoid technical bias, which is pretty common in our environment. So what is the solution? To complement the technical perspective with the main stakeholders one. And it means that these stakeholders are empowered to participate in the definition of the requirements and the main functionalities of USWA. So here you can see two main flows, the green one and the blue one. We have a lot of information to start, which is the USWA proposal, meetings, market analysis, standards, assets, previous knowledge of the people of the companies involved in USWA. So taking this information, we have defined preliminary use cases. With these preliminary use cases, we have defined descriptions, mockups, and several reports and information in order to interview and make focus groups or conversations with the main stakeholders in order to have and infer the stakeholders' perspective. On the other hand, we have the most common path, which is with the preliminary use cases. We have defined the technical part, the technical definition, and we have the technical system perspective. So merging both, we have created the main requirements of USWA. In order to communicate the requirements, we have used the Volere methodology. Here, with this methodology, they have one language, let's say, used for management of this kind of requirements, and we use it to have this common language among the USWA partners. The Volere requirements specification template is intended for use as a basis. and we have adapted it. Here we have our own adaptation. And as you can see, we have the system perspective and the stakeholders one. The system perspective has several fields: the name of the requirement type, a brief description, the justification of the requirement, the main KPI in order to validate it. Here we have the priority, which is the order to classify and infer the importance or implementation order. And from the stakeholders' perspective, we have the customer satisfaction and dissatisfaction. They defined the degree of stakeholders' happiness if this is successfully implemented, and the contrary, unhappiness if this requirement is not part of the final system. Giving an example, if we have, for example, a payment system and the payment itself is a requirement, the priority in the system perspective must be 5, because we need to do that. However, the customer satisfaction could be 1 or 2, because it's commonly accepted. But if the payment is not performed, the customer dissatisfaction is going to be the highest value. In this case, 5. The other pillar was the use case centric definition. This is one approach to capture information about how the system should work and to define the main functions and tasks for the system in a particular environment. So keeping these things in mind, we have defined these use cases, and we have one more time one table to normalize the information, to have each use case with the same fields and make them comparable, groupable, manageable, more manageable and simplified. So here we have the main name, the use case type, actors, objectives of the use case, a brief description of that, the justification of the defined use case, why it's important, and other fields like the partners who have defined that, the version of the table, and these things. Okay, here we have the use case type, which is one of the main fields we have defined, because we have defined 6 main groups. Here we have the electricity network quality of service monitoring, condition monitoring in industrial facilities, wireless transmission of audiovisual media, off-highway vehicle control, and wireless communication for robots, and also tracking and location use cases. Okay, let's go to the requirements, and after that we are going to talk more in detail about this kind of use cases. So the defined requirements are the security, which is the requirement to protect industrial data and equipment and ensure secure communication to avoid financial and safety risks. The graphic interface requirement enables users to visualize and intuitively analyze data to make informed decisions, for example. The device density is the number of wireless devices operating within a given area or network. It is important because high density of wireless devices can impact the network efficiency. So the system must be prepared to manage that. The range or coverage area is important to enable reliable communication between devices in industrial environments, because without the enough range, device may not be able to communicate with each other. It produces sometimes critical impact in the network effectiveness. The reliability is crucial. It refers to stable connections without interruptions or data errors. It is essential in industrial settings to avoid costly downtime, to ensure safety, and to have accurate data, which is very, very, very super important there. in this kind of environments. The latency is a key requirement as well in industrial communications, in particular for precise and real-time control of production processes. The latency here is considered as an end-to-end latency in all use cases, and it ensures the system reliability, efficiency, and safety. The jitter is the variation of one-way end-to-end time delay. So low jitter avoids delay-related failures in the system. The throughput or transmission capacity is in industrial communications is important to ensure reliable transmission. So several use cases, such as the media ones, requires the transfer of large amount of data. And the mobility is the speed the devices communicating over the radio link can be moved without significantly impacting the network performance. Here we have the availability, which is a general requirement for the IoT devices to be able to communicate within the expected time frame, and it is essential for many use cases as a basic system health parameter. The power consumption of the DEC 2020 new radio networking is sometimes crucial because the devices, or maybe part of the devices, does or do not have a power supply or large battery. And the next one is the location accuracy, which is fundamental in asset and people tracking, as well as any other location-based use cases. And last but not least, the legacy interoperability is key when enterprises are looking for solutions that work with legacy environments and systems, because that systems represent the major investment. So that's the interoperability between the new systems with the current or the old or legacy applications is a common problem that must be solved. And that's all the requirements. So let's continue with the use cases. Here we have the first one. The first use case group is focused on wireless technologies with grid management. We are talking about deployments of sensors and equipment in remote areas. So here, machine-machine type communications and ultra-reliable low-latency communications provide services like metering, asset management, fault indication, and predictive maintenance. Everything in substations and between transformers. Here, the time-stamping and synchronization play a vital role. So here we have a couple of examples of consumption monitoring. The electricity consumption monitoring integrates this technology in electricity consumption monitoring system to allow connectivity and scalability of the platform of the system. So here we have a high density of devices and the legacy interoperability as well. On the other hand, we have we would like to monitor server rooms electricity consumption in real time. So here the critical communication is a key. So latency and jitter must be low. The environmental monitoring use cases are to obtain periodic updates of environmental data. So here the latency and throughput are not very strict, but we have a device density because we would like to monitor a lot of environmental variables. On the other hand, we have more or less the same, but focused on the video streaming. So here it requires low jitter and delay, and the throughput as well is very well. Here the throughput requires a high throughput. The device health monitoring are to monitor the behavior of the machines. So here we would like to design and implement a wireless mesh network for collecting vibration values from sensors So here is the battery life is very important. Also, we are going to deliver a low amount of information. On the other hand, we have more or less the contrary, because we are going to design another wireless mesh network for connecting smart devices. The battery is also important, but here we would like to create a harsh environment, let's say. Focusing on the main requirements, the most important one is, in general terms, is the latency, followed by the jitter and transmission capacity. Surprisingly, the power consumption is not so important in general terms, neither the location or mobility. And from the stakeholders' perspective, we have almost the same results. Just highlight the mobility requirement that here is, let's say, a nice to have requirement. The next use case type is the conditioning monitoring. The condition monitoring systems provide diverse data to control systems using novel technologies such as artificial intelligence. It requires a lot of data, and thus the connector sensors, actuators, and IoT points are expected to increase a lot. It needs efficient communication and data transfer to effectively manage that growth. So it means we need to add new solutions to deploy add-on sensors, provide easy installation, manage the radio spectrum, and so on. Here, the key is that it needs new solutions designed specifically for industrial requirements, not modified consumer products. Here we have one example. Here we would like to design and implement a wireless mesh network for connecting smart devices in this kind of environment. And here we are going to have intensive data produced by several devices and machines. Here we are going to develop predictive maintenance, monitoring platform, with security platform, wide range of applications. From the use case, from the requirements perspective here, the technical perspective and the stakeholders one are similar. The range, throughput, and device density are the most important ones, which are the ones focused on warranting the delivery of intensive data produced by a lot of devices. Furthermore, these requirements are followed by the power consumption and latency. It means that real time is not primary, and that power consumption impacts in terms of costs, given the amount of devices to maintain in industrial facilities. The next one is the wireless transmission of audiovisual media. So the main aim is to achieve immersive media production and broadcasting using DEC 2020 in order to provide immersive media to live events and streaming, permitting audience to virtually attend live shows, to see live information of the programs they are seeing, sports activities, and this kind of applications. So here in USWA, we would like to enable secure and reliable conferencing system in post-quantum era. Focusing on the requirements, here the security is a must. As you can see, not only the technical perspective, but also in the stakeholders one is key. So going back to the payment example I mentioned explaining the requirements table, we have the same situation. The lack of security leads to a very unhappiness because it's a must for the customer. The availability, reliability, latency, throughput, and range are also important. And it is not rare we are transmitting audio, so it's there are the requirements to transmit this kind of data. And the lack of priority for power consumption, device density, and mobility implies that we are facing use cases with few but powerful and almost fixed devices. The off-highway vehicle control refers to the management and control these industrial kind of vehicles in construction, mining, farming. It will require real-time data transmission, precise control commands, and remote monitoring. Here we would like to develop 4 main use cases. Here is one, which is mainly to provide the connectivity using DEC 2020 new radio in order to remotely control these heavy vehicles, using video, using safety protocols, in construction, agriculture, mining. Surprisingly, here the location accuracy is not key, neither for the stakeholders. However, the device density, mobility, and range are 3 of the most important requirements. These ones describe very well the environment of these kind of vehicles. Also, the reliability and transmission capacity are super important as well. The next one is the wireless communication for robots. They are focused on enhancing robotic capabilities in industrial settings, replacing traditional cables with wireless communication. With this approach, robots can achieve greater mobility and flexibility, and we can reduce the economic impact of deploying hundreds of meters of cable. This use case type aims to enable seamless data exchange, real-time communication, and synchronization between robots and the surrounding devices. So aims to provide scalability, to reduce the maintenance costs, and we would like to improve the sensor integration. Here we have several examples. For example, the first one, the ever-changing factory, we like to shift the location and mapping algorithm from the mobile entity into a cloud environment. So here we need to adapt several interfaces in a critical communication security environment. The teleoperation for robots demonstrate the post-quantum cryptography can secure wireless ultra-reliable low-latency communications in this kind of environment. So here we have the strict synchronization between the devices. The authentication should be must be fast and secure, with a fast and secure handover. And here in the third example, we have the industrial operations in harsh and noisy environments. We would like to add this technology to sensors using this kind of technology to a cobot and measure the behavior as compared to wired deployment. Here we would like to have very high interference environments, and here the critical communication security and reliability plays a vital role. So as we see, the security is one of the musts in this kind of environments, also for the stakeholders. And here the critical communication security and reliability requirements are most important. The reliability, the latency, transmission, capacity, and range. Jitter is out of the main priorities, but more or less the critical communication security and reliability is very, very, very super important. The device density is another requirement to satisfy. given that the industrial robots have a lot of sensors, actuators, and a lot of surrounding devices. The last one is the tracking and location. The tracking and location refers to use cases when the main application is based on tracking and following possible movements of several assets and people. The goal is to find assets without time-consuming searching, monitor them to react to possible deviations, and provide applications based on these premises. Here we have two main use cases. The first one is based on collecting RFID data from RFID readers in a construction environment. They are going to be configured remotely, as well as the second use case. And here we are going to manage tens of thousands of readings at the same time. So here, the security and reliability are super important, as well as the location the location accuracy. This is because if we do not gather the correct information in a reasonable timing, the cost damage could be catastrophic, including personal injury. If we are talking about, for example, in a construction environment. The reasonable timing is not very strict because the latency is secondary and jitter is out of this use case scope, but they are also important. The device density is also important as well, probably because the managed assets are a lot. So to conclude, here the technical perspective says that the latency is the most important requirement. The transmission capacity is the second, followed by the range and reliability. And here the security and availability are not a common requirement, but have a very high priority here when it appears. So here you can see the security and availability as well. And from the stakeholders' perspective, more or less, we have the same, because the latency and transmission capacity are the most important requirements. And they also make the most dissatisfaction of the stakeholders. We have the jitter, which is the requirement that changes more between satisfaction and dissatisfaction. And range, reliability, and device density are also the primary requirements from the stakeholders' perspective. So to conclude, here we have a couple of numbers. We are going to deploy 18 use cases, distributed in 4 countries and classified among these groups. We have 4, 3, so more or less we have an equitative distribution in the use cases types. That's all. Thank you so much. And here we have my email and my colleague Ndikas, who is another important person or contributor or inside these works. And I'm right now open to your questions.
So now we have some time for immediate questions. So this was like a high-level presentation of top-down use cases that we are investigating, how they would match and what kind of requirements they would set to the radio communication and the overall system. If no questions, we are nicely on time. So then we would move to the next one, which would be the Oli Kafali from ACD presenting the challenges of wireless solutions in industrial environments. So,
thank you, Juho.
Please
Thank
go
you
ahead.
very much. Today, I'm Ali Kafalı from ACD. I'm working as a R&D manager in ACD. Today, I would like to explain some challenges of wireless communication in industrial environment and some solutions. Outlines is the importance of wireless solution in industrial environments. And there are some challenges, especially wireless solutions, in terms of communication challenges between the machines and robots used in industry. Different protocols, challenges, and also the monitoring the machines and autonomous robots for end user. There's some also challenges here. Also data storage challenges, especially in factory environment, security solutions, and I would like to talk about some feature trends. Sorry. Today, we put the three pillars in the importance of wireless solutions, especially in industrial environments. We need to increase, first of all, efficiency in terms of optimizing the operations in wireless solutions and minimizing the manual interventions. Especially the second one is the flexibility, which is very also important for reconfiguring the wireless systems and adapting to some dynamic industrial environments and changing requirements. Sorry. Another part is safety. And also this is a very important part for hazardous manual inspections and remote monitoring and improve safety outcomes. Now challenges of wireless solutions in industrial environments. There are some headlines here in terms of reliability, resilience, scalability, and latency. So we need to improve some security, network requirements, and harsh industrial environments, and RF communication characteristics also very important part of these solutions. Communication challenges related to machines and autonomous robots, especially there are some standard communication protocols, but there are different type of solution in the market, so needs to be supported the standard communication protocols. And another thing is that sensor and actuator incompatibility. This is also another important part. And delay and real-time communication, software and firmware compatibility, also security and data privacy is also the big challenges in the communication part between the machines and autonomous robot in industry. In terms of protocols, so there are some protocol diversity and compatibility about incompatibility and integration difficulties between different protocols, and also communication speed and data transfer. So difficulty of harmonization between the standards ensure fast and effective data transmission. The lack of standardization, machine type independence, and security and data integrity. These are the main challenges of the supported protocols. The Challenges of monitoring machines, robots for end user aspects. There are some also internet connectivity problems, management of real-time data flow, sensors and data formats, data analytics and meaningful information extraction is also key parts. And also there are lots of big data management and storage, especially in the customer aspects. So they like to store all these entities within the big data infrastructure. So as the data storage challenges, especially for example storage capacity, data accessibility, and also the backup and recovery part is also the crucial to prevent data loss and maintain operational continuity. Internet communication challenges in terms of security. So network vulnerabilities and also interconnected nature of industrial internet introduces lots of vulnerabilities that threatening the actors can exploit, posing significant security risks. Another part is also data encryption. Implementing robust encryption techniques essential to protect sensitive industrial data over the internet communication channels. And another part is also the identity and access management, which is secure identity verification parts and access management to prevent unauthorized users for the critical systems. And there are some solutions for industrial wireless challenges needs to protocol standardization and integration. Wireless network security solutions also should be implemented within the industrial wireless solutions. And also another part is mesh network, which is also a very important part for the especially mobility aspects to communicate in each part of this manufacturing area. Industrial IoT integration is also a very important part. And protocols for machine and robot communication, some solutions there. Also the big data analytics and storage solutions, energy efficiency solutions, data traffic management, and secure internet communication solutions should be implemented within the industrial wireless communication part. So future trends is when we are talking about environmental energy efficiency. So there are some 5G integration and 4.0 industry is needs to communicate in each part of this entities, and also edge computing and wireless networks is also another part. Industrial IoT, also standardization, cybersecurity, sustainability, and advanced communication protocols. And AI-based solutions for wireless optimization is another part of this future trends within this for these solutions. So the conclusion is challenges of wireless solution in the industrial environments are significant, but with innovative technologies and solutions, These challenges can be overcome to unlock full potential of wireless communication in the industry. Thank you. If you have any question, you can ask me. And then my email on the presentation. So you can ask me every time if any type of questions. That's all from my side.
Okay. Thank you, Ali.
Thank you.
Thank you. So I summarize now where we are. So we have now seen a little bit that what kind of analysis we have been doing, use cases, and also that let's say the multitude of challenges for wireless and IoT solutions in the factory, and how many different aspects different solutions needs to take into account so that they can be deployed. The good part is that we are well in schedule at the moment, but now we would perhaps turn our presentations more on the stronger or deeper technical focus. And the first presentation from that is from Jukka Talvitie on the positioning aspects of ETSI-Tech 2020 new radio. Something, of course, completely new as the positioning has not yet been, for example, addressed in the standardization. So, Jukka, the stage is yours.
So, yeah, thanks, Juho. So, yes, the next topic will be going to the positioning aspect in ETSI-Tech 2020 NR. And here in this presentation, we will take a look at all the, let's say, possibilities and certain aspects on how to take these specific TEC NR, let's say, targets and use cases into account when designing the positioning system. And first, we will check briefly what kind of positioning measurement accuracies we're able to achieve in ETSI-Tech 2020. So what does it mean is that there is basically certain theoretical framework that can reveal the possible, for example, angle estimation or ranging based accuracies. And from there, we are able to deduct that what is then the maximum achievable positioning accuracies. And of course, in ETSI-Tech 2020, there are certain limitations on the bandwidth and certain let's say, practical limitations for devices. For example, having a certain number of antennas in the device is something that is of course limiting then for example, the angle-based measurement accuracies. Then we will basically focus on these certain important positioning aspect, which is selecting the measurements to reach this best positioning performance. So we are able to show that there are certain strategies that optimize the positioning performance depending on which actual measurements we use. And for example, in practical situation, it could mean that when the device that is going to be positioned, when it's located somewhere and it has certain anchors where the measurements can be taken for the positioning, it can select based on certain prior information the best possible measurements, which then results in, for example, reduced overhead and reduced power consumption and so on. So this is one of the important aspects in this presentation. Then in the very end, we show some example positioning results using some practical estimation methods, specifically this Kalman filtering based performance, and we show that what is actually the benefit on choosing the measurements in a best possible way. But first, I'm not showing, you don't have to be scared in that sense that I'm not going into any kind of a mathematical details or derivations, but what I will do is just to explain that how to how these certain measurements and certain accuracies, how the theory considers those. So basically, we have this Kramer-Rao bound, which is generally for any kind of an estimator, and in positioning, basically we estimate angle of arrival or time of arrival. So based on these theoretical bounds, we are able to say what is the best possible accuracies that can be achieved with the specific, let's say, parameters in the system. So first, we'll focus on time of arrival measurements. So time of arrival means that we basically measure the propagation delay, so time between transmitter and receiver. And in these kind of systems, in practice, the clock is always something that is a challenging thing to solve. There is a quite often a misunderstanding that if there is no information on the clock between the actual device and then the network or the device who is helping with the positioning measurements, the clock offsets are typically not a big problem. So they can be compensated by taking multiple measurements from different devices. But I guess one of the biggest challenges is this clock drifts, that basically means that the clock is evolving in time. And when that happens, it's very difficult to control and requires some specific attention on the system. But anyway, if we are assuming perfect clock, we are able to draw these type of performance curves as shown in the figure left. So there is an SNR x-axis on the bottom, and when the SNR improves, we are going into smaller error values. So on the y-axis, you see the standard deviation of the error when assuming it's normally distributed. So this in DEC 2020 specifically, there is these certain numerologies, certain, for example, subcarrier spacings, different combinations, which then result in different bandwidths. And in timing measurements, the bandwidth is the key thing to consider. So the bigger the bandwidth, the better the timing accuracy. On the right-hand side, you see these color mappings. So for example, from the red lines, we have plotted the kind of a minimum and maximum bandwidth. So for the subcarrier spacing of 27 kilohertz, we have this roughly 1.5 megahertz bandwidth up to 25 approximately. And then the two red lines, the continuous and the dashed line, show you the performance in the time of arrival accuracy. And of course, the bigger subcarriers you go and the bigger bandwidths, the performance can be then improved. And same type of measurement accuracies on angle measurements can be shown for these different SNRs. And in this left curve, you see the Kramer-Rao bound for the angle of arrival estimation with certain parameter combinations, varying the number of antenna elements, which is the L parameter in the legend and in the curves, and the D parameter, which shows this separation of antenna elements. Lambda means the used wavelength. Here we have assumed 1.9 gigahertz carrier frequency. And then there is this alpha, which is the actual true angle value that we are estimating. And in angle measurements, it's a specific in that sense and different to the time of arrival, is that the actual true antenna, the true angle of arrival value really affects also the accuracy. This is because of these certain, let's say, angle resolution at the multiple antenna systems. So when we have multiple antennas which are then used for the angle estimation, it's always good that if you have the angle directly ahead you, then the angle or the measured angle like from 90 degrees from the center. So that's actually giving you infinite error basically, because you cannot really say it's symmetric to the plus and minus 90 degrees. Then, let's say the main thing is that when the number of antenna elements is increased, so the L here, we can always improve so basically that increases the angle resolution. And also then with the antenna separation, we are able to improve when we are putting the antennas more far from each other. It basically improves the accuracy, but allocating larger than this wavelength divided by 2 antenna separation means that we will have a basically unambiguous estimate, and meaning that we see these multiple so-called likelihood peaks where the angle can be, and that is typically considered as a very large problem. But it has to be also noted that we can use that to improve the angle estimation accuracy. And on the right-hand side figure, we have fixed 4 elements and the antenna separation into this very conventional lambda per 2 value. And then with different actual true angles, when we are measuring, you can see the differences. So zero angle gives the best performance. 45 is still very close, but then when we go to the plus or minus 90 degrees, we are facing trouble. And what does it now mean from this presentation point of view? Well, it means that depending on where we are, so what is the angle compared to the reference device that we are measuring in, defines although the accuracy of this measurement, and therefore it also affects the positioning accuracy. Here is then extension of these time delay measurements and angle measurement based estimates now to the actual positioning problem. So in this case, we have 2 examples. On the left, we have these angle measurements, and on the right-hand side, we have these time delay based measurements used. And then there are, in both cases, it's an identical networks. There are 3 of these anchors or base stations or whatever we call those. Typically, devices whose position is known. It doesn't have to be precisely like that, but that's the typical assumption. And then the device is somewhere here in the area. And now, depending on where the device is, the positioning accuracy is different. So the deeper the blue color, the better the accuracy. So basically the so-called positioning error bound, which gives basically the standard deviation of the error distribution, is color given here on the color bar. So the deeper blue color means closer to 1 or below meter error here on the angle measurement. So where we happen to be inside this basically this triangle formed by the anchors, we are having a good performance. But when we are going outside, the performance is decreasing quite rapidly, actually. And same here there is eight antenna elements used in this example. It basically affects this scaling of the positioning error. And then here on the right hand side we have a similar figure, but now using timing measurements. So again, the deeper blue gives you better performance. Here this scale of the colors is now in totally different ballpark that with the angle measurements. So time delay measurements are actually really accurate, and they are really can be used really efficiently in positioning compared to the angle. So in the angle domain, we would need to increase the array sizes to very large, and that is typically, of course, limited by the device sizes and so on. But of course, we have to remember that on the right-hand side figure, as I already explained, there is the clock errors and those which can severely affect the positioning accuracy. But again, this figure shows the positioning accuracy as a combination of these different base stations, but we can basically always also calculate the positioning accuracy per one base station if it's just possible from the measurements point of view. For example, here, when we have now combined the two angle and time-based measurements, we can see figure like this. And now you can see that we are in basically sub-meter accuracies in this area, always in the area of base stations or between the base stations, and it's much more, let's say, stable from the positioning perspective. But now in this case, because we have this time or basically range-like measurements and angle-based measurements, we are all able to actually do the positioning with one base station only. I have not put any results on that here, but that is now possible if we have both angle and range-based measurement in use. There is also one very important measurement which is kind of used generally in many networks currently to do positioning, and that's the received signal strength or path loss based measurements. The problem in these measurements is that they are not very accurate. But for example, for, let's say, Wi-Fi based indoor positioning, it's possible to reach a few meter accuracies. For outdoors, close to 10 meter and below accuracies in these urban environments and so on. So it's still very close, very good accuracy and let's say sufficient accuracy in many use cases. And the benefit of that is that it's typically anyway measured as part of these radio processors and radio resource management in all the networks. It is basically, for example, in mobile network, it is used for the mobility management to say that which of the base stations have the best power and so on, and doing handovers and cell reselections and so on. So here also now, if we consider the specifics of the DECT NR system, there is many times, for example, power constraints, power consumption constraints, and these things that we need to take into account. And RSS measurements, if they're anyway taken as part of the regular operation, it's kind of almost a free lunch for the positioning. So it's a very interesting case. But here on the figure you see these ranging accuracy. So it's now in meters, and now we are, as you can see, we are in totally different level than with timing based measurements. and here there is the path loss propagation exponent on one of the axes, 1, 2, 3, 4, 5, and then the actual distance of the user. So the user distance is affecting to the accuracy. And now the smaller is the path loss exponent. So when we go towards, for example, free space loss, which is a path loss exponent of 2, so basically power of 2 loss in distance. So you can see that the ranging accuracy will kind of skyrocket quite fast there. But if we are in more dense environments, for example, indoors, dense urban environments with higher propagation exponent, the ranging accuracies remain in a sensible level. And also here, the distance, so the actual, similar as in the actual angle depends on the accuracy, and here the actual distance depends on the accuracy of the measured distance or the estimated range. And the smaller is the distance, the better is the accuracy. This is because of this path loss model here, which is in assumed here as this log distance path loss model. This is very typical and also quite practical model in most of the systems. So, but here anyway, the problem from the ranging accuracy point of view is that if we are very far away, the accuracy will drop. And then here there is a example on these power-based measurements and what kind of a positioning accuracies we're able to achieve. So on the left-hand side, we have actually the same case that we had with this time and angle-based measurements. So with 3 anchors, and you can see that we are in a few tens of meters accuracies in the in the main area, maybe reaching close to 10 meters. But if we have more anchors, so these are totally randomly selected, on the right-hand side with 10 anchors, you can see that this error is reduced quite a bit. So now we are all the time below 20 meters, and basically in this regular or center area in the system, we are below 10 meters, and that is already really good positioning accuracy if we think about the fact that these RSS measurements are anyway taken occasionally and measured between the devices that can provide a good performance. But then to the actual let's say specific strategy on the positioning on the specific TEC 2020 mesh-like network. So as mentioned, here we focus on this idea of selecting the best type of measurements and the best devices from which the measurements are taken. So basically, if we are first focusing on a theoretical way framework, it's actually very easy to say that there is this best measurements, because each measurement can be shown to have certain information that we can take from the measurements. And it is therefore a fact that certain measurements actually bring very small amount of information, whereas certain are actually crucial for the best positioning performance. And then we can actually do the positioning in that way that we take first the measurement which provides the kind of the largest part of the information, and then slowly accumulate measurements from the other nodes as long as we find the, let's say, performance that we're looking for example. So why to do this is that I mentioned already a couple of things, but maybe good to emphasize. So first of all, the signaling overhead. So the more measurements are taken, the more signals we need to transmit. And of course, if we are able to reduce the amount of signaling, then we are also reducing, for example, the system interference. At the same time, we also of course reduce the used energy, which is the third bullet, improve power efficiency of the system, because whenever we minimize the transmission, we minimize the used power. We reduce latency because we don't need to wait or take an excessive number of positioning measurements, as or we can say that, okay, only these 2 or 3 measurements are actually enough, and the 4th or 5th measurements are then not actually providing too much information anymore to the positioning solution. We reduce the computational load, so the less measurements, the let's say more straightforward the algorithms and the computational burden to kind of crunch the bits to find the actual estimates. And also we can design a certain positioning target. So for example, in 5G NR, there are certain these positioning service levels which define certain accuracies, latencies, and so on. And now with this strategy on selecting certain measurements, we are able to select as many measurements as we need for the certain performance target or service level, as well as to, let's say, face certain latency and reach certain latency. So if we are taking too many measurements, we are not necessarily fulfilling the certain latency requirements depending on the system. But okay, let's then go to the actual example. What do we really mean by selecting these measurements and how to do it? So here is a very simple example scenario. There are anchors shown in a blue rectangles, and then there's the user device, which is now here given as a red point in the center, and then the so-called positioning covariance or this error ellipse. So we estimate that the user is within this region, and this is basically referring to this prior information together with the mean and then this ellipse around it. They are basically 2 numbers which define then the prior information of the user position. Well, not 2 numbers, they're actually 5. Well, depending on the dimensionality, but this is anyway the case. So very simple idea of having this prior information. And where do we get this prior information is, for example, through tracking processes. So we, for example, here could know that at the previous time moment we were somewhere here, and then we moved further at this time step, or we predicted that we are here, and so on. And now if we have this prior information in known, so the basically the known or estimated position, well, it's a little bit wrong to say that with the known position, because then we don't need to do the positioning at all. But if we have estimated the positioning at certain accuracy, then we are able to use and define this information based on so-called Fisher information, which is related to actual this Cramer lower bounds directly. And if we assume that these errors are Gaussian, which is commonly assumed, for example, in this Kalman-based filtering, or then they are actually linearized to Gaussian distributions in these Kalman-based filters, then these calculations are really simple and easy for the device. So we can basically this Fisher information, it can be used in both line of sight and non-line of sight scenarios. Line of sight is much more simple, but in non-line of sight it is certainly possible, and then it just requires more computational power to reach the desired result. Here's an example of ranging measurements. These are not numbers from, well, the parameters are taken from a hat basically, but then the actual numbers that I'm going to show here are really realistic and coming from simulations. So here there is a setup where there is 3 base stations. One here further away from the user, which is with the red dot here. The further away base station or anchor has a signal to noise ratio of 3 dB, and then the closer ones have 17 and 20 dB. So with higher SNR, therefore the closer one can reach better positioning accuracies from the SNR point of view. So they're able to estimate the angles or the ranges better. Here we focus on the ranging measurements. So that's the focus here. On the left-hand side, we choose 2 leftmost anchors, and we then don't take measurements from the third one, which is further away. And we are able, with this ranging, we are able to reach about 3 meter positioning error bound. Whereas then on the right-hand side, we take a base station from the right-hand side from the user, and then the one further away. And that gives basically 2 times more accurate positioning result, even though that the SNR of this further away base station is much lower. So that is in a sense interesting, because then it gives us instantly an indication that this SNR is not actually the best selection strategy for the base stations, but it's really related to this kind of a geometry of the base stations. So why this is happening is that I could even try to draw it here. So when we measure the range, we are measuring these circles around the base station. On the left-hand side, there are 2 circles like this. And now the problem of this is that this intersection point between the base station is not very clear, because these 2 circles are basically they are basically parallel around this base station. But then when we go to this figure here, when we measure the range from here and then the range from this further away base station, the intersection point is clear. And this is now the main reason why this 2 times more accurate measurement is possible, even though that the SNR is much smaller. If we choose all the anchors, the result will be basically 1.3 meters. And if we think about 1.3 meters and go back, it was 1.46 here. So only about 15 centimeters more accurate than earlier. And then what is basically the price in the system to take the third measurement? That's another question. But with 2, we can already reach basically the same kind of a positioning performance level. And therefore. And then to the end, I'll show basically a more practical result on this specific positioning strategy by which is focusing on selecting the best measurement. So in this example, we are creating a system where there is basically user nodes, anchor nodes in this 690 meter radius area. The distribution of nodes is uniform, and basically there is 25,000 devices, from which 4% are actual anchors. The path loss parameters are chosen based on this urban micro path loss model taken from the 5G NR specifications. All the anchors who have SNR below 5 dBs are basically neglected, although positioning measurements can be taken, but there is basically then no this communications capacity assumed there, so no signaling exchange can be done. But basically the positioning signals could be still utilized with even with minus SNR values. We assume that there is a user who's moving at speed 1 meter per second in the area, and here the measurements are taken at 10-second intervals. We have considered relatively low measurement interval here to focus more on this low power consumption environment, but definitely higher time resolution is certainly okay. But then if we have a mobile device, basically the speed of the device is somehow indicating that what should be the measurement interval. We cannot then track devices if they are, for example, measured every minute or every 10 minutes if we move around. So then the prior information from the mobility is not really there. We have assumed 10 megahertz bandwidth and with 4 antenna elements, and we add these small errors on top of the kind of theoretical limits to consider this clock variation and antenna impairments, for example, in the relative phase between the antenna elements and these things to have a more practical results. Here you can see the track. It is this yellow line. Well, the true track is actually the red line, but you cannot see it because the actual end result is basically on top of that. The area is very big, so there is a zoom on this one point here where you can see the true track with the red color, and then the estimated track with the yellow one. And in the estimation, we have used this extended Kalman filter, which is a very conventional estimation and tracking method for positioning in general, used in many systems. So it seems very accurate. If we see the actual positioning accuracies, if we focus on time delay measurements and see what is the accuracies with those in the area over all the anchors, over all the points in the track. Here is a cumulative distribution of those. So we can see that we are well below 1 meter error. So even with 10 megahertz, it is definitely possible, and there is even a small clock error there, that it's possible to reach really nice time delay measurements. But then the practical challenges, as I mentioned many times, come from the clock and managing the synchronization. With angle measurements, we basically have a sub-meter accuracy for 90% of the measurement. So we kind of across cross the 1 meter positioning error at 90% here, whereas with the timing it's like about 17 centimeters and so on. But of course these are simulated results, and they are probably not the most realistic ones. If we consider this mobility and the basic idea how we use this prior information to select the measurements, with the Kalman filter, just like in the example shown below, we are able to gather this information based on the predictions. So when we have estimated the user position at certain time t, the Kalman filter basically, or any kind of a tracking filter, is able then, based on the assumed mobility model, it's able to estimate where we are going to be at next time moment where we take the measurements. So we can already basically pre-plan the measurement set. For example, here if we use 10-second measurement interval, we have 10 seconds time to design which of the measurements are taken, because we can already predict where we are going to be in the next time when we take the measurements. We can also, the model, we can have also the possibility to move the anchors, but again it increases the complexity, and we haven't yet considered that in this presentation. But that's the main idea. What is the mobility model? Of course, depends on the use case. If it's in the vehicle, we have certain limitations. You can imagine that if you're walking on the street, you're not able to go 100 meters per second speed, but you're able to turn fast, go backwards, and so on. If you're driving car in urban area, you're able to do relatively fast turns, 90 degrees, for example, in cross sections. But if you're on the highway, you cannot do those relatively fast. So you're limited by the dynamics of the system always. And then to basically, I guess one of the main results are here, so that if we now consider selecting the measurements in the best possible way, what is the performance gain or the compared to the methods where we select the measurements based on SNR. So always take the measurements from those anchors who have the best SNR, or then just randomly pick the anchors. That is not very sensible, but it is included here because sometimes it actually can be even better than the SNR. But here on the figure, on the x-axis, you see the number of chosen anchors. So in the setup, it defines how many anchors we use in each measurement. For simplicity, we have selected it so that always in every position we use, for example, 2 or 3 or 4 or 5. Not that is not changing in time. Of course, in practice it can change in time, but here just to show what is the effect of how many anchors we use, it's shown here. There is 2 curves in both figure. On the left-hand side, you have the time delay-based measurements, so basically ranging, and then the angle-based measurement on the right. SNR method is basically meaning that you select based on the SNR, highest SNR anchors are used, and randomly means just randomly from all the anchors that are possible to use in that case. And then on the y-axis, it's a bit weird axis, but it shows nicely because I've already shown the absolute positioning accuracies on the previous slides. This shows what is the actual increase in accuracy if we now would not do the selection made based on the information as proposed. So if we would use SNR with 2 anchors, it's almost 250% higher error in the positioning. But when we have more and more anchors to be used, already in 3, the difference is 50%. So for example, if our positioning accuracy is 2 meters, with the SNR method, it is actually 3 meters. So this shows what is the increase in error if we don't use our proposed information-based selection. And on the random, then here it's a bit weird is that with 2 anchors it is actually better, but this SNR is sometimes making bad decisions, as we showed in the one of the examples earlier. If those 2 base stations that are close by, if they have bad geometry, it is sometimes forcing to do measurements in a poor way, and depending on the environment and so on, sometimes random can be actually better. And on the angle-based measurements, now the improver in the SNR-based method, SNR is working much better. So it seems that these ranging-based measurements are more, let's say, subject to these bad geometries than the angle-based measurements. But all of these results are really dependent on the parameters that we use. But it shows clearly that picking the measurements is really important from the system accuracy point of view. Just a practical note in the end that we can consider also the uncertainties of anchors. Some of the anchors can move, they can have errors in their positions. Some of the anchors can be assumed to be perfectly known, and so on. So all of these can be included also in this information-based measurement selection. So that's it from my side. I think I spent some time. So again, if there's any questions, I'm happy to ask. And also, if you have any questions, there's the email that you can directly even send questions to me.
Okay, so thank you, Jukka. So we still have, we are in schedule nicely. So any immediate questions? Well, my only question would be that I would be, of course, interested to see your simulation results that you were showing with the time and the angle-based measurement in this kind of large deployment, that how the RSI would be compared to that. That would be also, because that would be, of course, the most simplest one. But okay, but no. I think it's very interesting presentation from my side, at least. So learning something new. So any question? Is there something in the chat? Let's check. No? Okay. So then we go forward. So then it's we turn to another set of simulation results, and the results we are going for the from Mirza Alam from Wirepass, presenting the ETSI Tech 2020 new radio for MTC communication, and showing the latest results on that area. And we are 10 minutes ahead of schedule, which is nice thing in overall. So we have the time. So Mirza, stage is yours. Please share the slide.
Just a moment. So, Iho, if you would like to introduce something. Yeah.
Yes, okay. So I made a very simple presentation. So this is our presentation. Mirza will go to the details, but basically we have been studying how this Tech 2020 new radio is capable of MMTC communication, and the main use case has been this kind of electrical grid and of the smart meters. And if you go to the next slide. Basically, what we have been trying to figure out is to find out the best parameterizations for smart metering in smart city deployments. Just to give a little bit perspective that how the simulations would fit in the real world. So I took the figure from Berlin city, from checkpoint Charlie, and turned the area of 500 meters from the checkpoint Charlie. So we are now presenting simulations in that kind of environment, basically. So industry in the city, city with not extremely high buildings, but high buildings and studying that kind of area. And basically, we are looking the simulation results in terms of package outage to sync, so the overall and as well as the overall delay. So how much data we can push to the system through the systems with different LPT period before the transmission solution before talk. So how long the device is measuring to enable to assess whether the channel is free, and then the LPT threshold values. So what is the minimum or the signal level that is considered that the channel is free, and then the base also that how the LPT measurement is actually done. And all the traffic that is presented in is Poisson distributed. So and the average packet generation is varied, and now Mirza, if you go to the more details on the simulation parameters and so forth, so stage is yours.
Okay, so thank you, Juho, for this introduction and describing everything, actually what we are going to do. And welcome everybody. As you know, I'm Mirza Alam from WebPass. So our deployment scenario is like this. It is a 500-meter radius circle, and around 3,600 RDs are deployed. I will not go everything in details, but the thing is, in the middle, you can see this triangle, and the thing is, there are 3 sinks here, and we have around 25% routers here, and expected cluster size is 14. So with this router, 14 members could be associated. And blue stars are the routers. Here, blue stars. Small circles are RDPTs. Green triangles are gateway. 3 sinks are there. So you can see then each sink basically 1,200 RDs are associated, and there are some spatial distribution of receipt power is there. You can check it later. And our TX power is 19 dB and carrier frequency is 1.9 gigahertz. So a little bit more information about the deployment scenario. So we have total 5 channels are used in the system. Each sink has separate channels, and 2 channels are randomly deployed among the RTs. And next hop selection algorithm is something like this, that need to be associated. You need at least 85.7 dBm power. And if multiple next hop choice with the above mean Rx power satisfies, if it satisfies this mean power, then the next hop is the minimum hop count, of course, from the sink. And if you see the same hop count for multiple routers that a node wants to be associated, then we will consider the best signal level from the router. And of course, if the best router is full of 14 members, then we will select the best. And all transmission with MCS1, there is no power control, no beacon loss, and there is no delay constant that for measuring the packet outage. And number of retransmission is limited to 8. So here is the random channel access for CSMA/CA. Very common things. So CCA means sensing or clear channel assessment. So red CCA means that channel is busy. So there is a packets we can think in the queue, and the node wants to transmit. So it senses the channel, and the CCA or LBT look before transmission, and it finds that okay, this is busy, and then it backs up randomly, and then again try, and it finds that channel is clear. So it transmits its payload, and SIFS interframe space, small interframe space is there, and processing time, and then ACK is transmitted, and one transmission process completed. So basically, what we did here is, as you mentioned before, that this CCA or LBT period, it's a very important element or ingredients in this random access channel. And we gradually change two things of this CCA. First thing is the duration of this CCA or LBT. And second thing is we change the LBT threshold gradually, and we check that how does it affect the performance. And other parameters are here that CV min for router sync is 15 backup slot, CV max is 1025, and one backup slot is equal to 41 microsecond. And another important thing is the performance is measured in energy saving mode. That is, nodes are not all the time transmitting and receiving. 70% is the activity period of 4-second beacon period. That is total 0.67 second it is active out of 4 seconds. So it is saving energy, but sync is all the time ready to transmit and receive. Yeah. So we measured the performance in two methods is used for channel assessment during this LBT. So to cross-check the results, trends of the results are similar or same, and also compared to channel assessment method during LBT. The first one is like this, that during this LBT period, suppose it is 25 symbols, the node sends the channel for the 25 symbols, and the interference are accumulated, and it has this threshold value. It compares the threshold value with its accumulated interference, and if it is below this LBT threshold, it immediately transmits. So here is the LBT duration and the packet outage, percent of packet outage, and the x-axis you can see that packet inter-arrival time means in every x-axis means 1, 2, 3 means in every 1 minute, 2 minute, 3 minute a packet arrives, application packet arrives in every node or each node. And y-axis is the percent of packet outage at the sync. And you can see the lines. That top line, blue top line means that 2 symbol sensing. Next one is 5 symbol, and so on. And you can see that if we stick to some packet arrival, inter-arrival time, suppose it is 30 seconds, my pointer is here 30 seconds. So you can see that around 15% of packet outage for 2 symbol, and it becomes 4.8 here for 15 symbol, and it is 1.5 for 25 symbol when the packet interarrival time is 30 seconds. And you can see that it is actually decreasing very fast, but after 25 actually it is progress is not that much fast. It is basically, it's a kind of converging. So the same phenomena we see for the rest of the packet interarrival time, and the narrative is that is longer the LBT duration. Longer LBT duration improves the system capacity, and other this association related things or mean quality is there, so you can check it later. And here 1 minute packet interarrival, actually how much packet is transferred to the sink. It is 20 packet per second, and 30-second interarrival time actually we are transmitting 40 packet per second. So for this case, basically with around 1.2 or 3% percentage of packet outage, we are transferring 40 packet per second to the sink for this that is LBT sensing measurement and LBT duration. But one thing is that threshold is minus 82 here. It is constant. So we are not varying this threshold at this moment. Just we checked that whether this LBT duration affects or not. Yeah. So the question might come that, okay, LBT, if LBT duration sensing period is too long, then actually it is eating the overtime. So it may affect the delay, but we can see that whether this LBT duration is 2 symbol, 10 symbol, or 25 symbols, that is the distribution of end-to-end packet delay is almost the same. Yeah, so it is not affecting the delay that much. So another thing, basically we are now wants to see that what about the LBT threshold, because before we saw that longer the LBT duration, better the results to some extent. So here LBT threshold, so just everybody, but I just quickly try to explain that how this hidden node problem appears. So suppose it is RDFT, red circle, and you can just 2 nodes are picked up, node 2 and node 1, and our minimum RX power for association is minus 85 dBm. So, and before it is mentioned that minus 82 dBm is the LBT threshold. So suppose this node 2 wants to transmit. So the node that is inside this LBT2 threshold value, actually those nodes cannot simultaneously transmit because there is LBT. That is, probability is very small that there will be a simultaneous transmission. But this could create problem because this is small amount, high amount of threshold will create problem, because suppose this node 2 cannot hear this, LBT cannot cover this node 1 and even RDFT. So it can transmit, both node 1 and 2 can simultaneously transmit to RDFT. So there will be a collision. And it could happen that suppose node 1 transmitted 1 packet, and after processing this packet, this RDFT is transmitting this ACK. At the same time, basically, this node 2 is transmitting 1 packet because LBT threshold tells that you can transmit. So it is transmitting. So the ACK towards this 1 will collide with this PDU packet by that is transmitted to this RDFT, PDU and ACK collision. So we need to think about this LBT threshold also. So from this perspective, we conducted a simulation, and it is for 15 symbol slot LBT duration, and this association is everything that is the same. And we can see that when the LBT period is -72 for this 30 packet per second on average is coming from each node. So we can see that it is around 7.2%, and you can see that it is going down as the LBT threshold value goes lower, or we are increasing the sensing range of the node. Yeah, so you can see that it jumps from 4.8 to around 3.7 or 8. That is from -82 to -89, and remains almost the same for this deployment scenario. So setting this LBT threshold lower level basically improves this system capacity. And it is for 15 symbol slot LBT. So same thing is checked for 25 symbol slot LBT. So 2 point is taken, that is LBT threshold is -89 and LBT threshold -82, and this is 25 symbol slot sensing. So we can see that and here is this x-axis is the average arrival time of packet. So we can see that -89 LBT threshold outperforms, and here you can see that packet outage is almost the same, 1.2 or something, and you can see that here 1.2. So when it is -82 for the same packet outage rate, we can transmit node can transmit packet in every 60 seconds or every 1 minute. Yeah, to keep this packet outage same. But for this only 3 dB, that is lower LBT threshold, basically improves this performance a lot. We can see that now we can transmit 10 packet per in every 10 seconds, but we can transmit in every 10 seconds. That is, it is a factor of 6. And also you can see that here is this factor of 3 improvement from this point to this point. So for both 15 symbol duration and 25 symbol duration, we checked that, okay, so if LBT threshold is smaller, lower, and then it improves the capacity or packet outage a lot. So now we will go to the second method of channel sensing. Just going to the second method of channel sensing, just quickly need to mention what was the first method. Though we discussed, the first method is this accumulating the interference for the entire period of sensing. But here actually it is a bit different. Actually, during this sensing period, it is taking sample in every symbol. That is, if we have 15 symbol, then 15 samples are taken from this 5 channel before transmission. And from these samples, every sample, it detects that if any sample has the transmission power higher than this LBT threshold. If it is higher, then there were some transmission happened in this LBT or CCA period. So it backs up randomly. And if it finds that there is no sample signal that is higher than this threshold, so it immediately start transmission. So it is the second method of channel sensing in CCA. And here is a comparison that is first and second channel sensing method, and it is 30-second average packet per device. 30-second average means in every 30 seconds it is coming because it is Poisson arrival process. So we can see that it is the first channel. The blue curve is the first channel assessment method. Second channel assessment method is the sampled version, and LBT threshold is in the x-axis, and we can see that for every or each and every LBT threshold value, the second channel method outperforms for this 15 symbol LBT duration. So it is good sampling in every sample symbol rather than taking accumulated interference. And we are going to our main thing, that is LBT threshold and LBT duration. So you can see here that we are studying it for, of course, for the second channel sensing method. So we can see that the red curve is 15 symbol sensing and blue curve is 25 symbol. And study is done for 30-second packet arrival, average packet arrival in each node. So we can see that first thing is that 25 symbol sensing duration outperforms. You can see here blue curves. And second thing is that is actually we are investigating that whether this smaller LBT threshold is good or bad. So we can see that lower the LBT threshold, better the performance. And you can see that even for minus 99, 25 symbol sensing, it is 0.5 percentage of packet outage at the sink. And just need to mention that we have 3,600 nodes covered by the sink, and that is 3 sinks, that is 1,200 nodes per sink. So everybody is transmitting, generating packet in every 30 seconds. Okay. So here is this observation. So observation is that it is very clear and not very, that is two things basically we tried to mention, that is there any optimum or good LBT sensing duration? And second thing, we tried to find out what about the LBT threshold value. So we see that LBT sensing duration 25 symbols or a bit higher is good. And we also found that sensing threshold around minus 89 dBm or bit lower gives good performance. And another thing, actually, we found that second sensing method gives good result compared to first method. And if we consider both method, both this accumulated interference during CCA or sampled measurement, we see that 25 symbols are a bit longer outperforms 15 symbol or shorter sensing. And of course, for both cases, threshold around minus 89 dBm is good. So one thing from this application perspective is that we can see that this DECT NR plus system, it can support a large number of smart meters within, as for example, 1 kilometer square area. So you can see also here. So you can see that packet generated in every 10 seconds means almost that we are transferring 120 packet per second to the sink. That per sink we have 1,200 nodes. So we are transmitting 120 packet per second to the sink, and every node is generating packet in every 10 seconds. And the percentage of packet outage is small. And another important thing that we are not using the whole bandwidth of channel. So nodes are basically using only 2 channels, and sink has 1 separate channel. So for this, if we use this full capacity or this full all this frequency bandwidth, then this value will be much higher. And still, if we use this 2 channel for this RD nodes and these things, 1 channel orthogonal channel for this thing, so we can see that we can transmit packet in every 10 seconds. But in electric meter or smart meters, that is on average, we can say that they generate packet in every 15 minutes, on average 15 minutes. So still we have a large unused capacity. So where node can generate every packet in every 10 seconds, that is interarrival time 10 seconds. So in general, we need just only 15 packet in every 15 minutes or like this. And you can see that one sink can cover a large amount of area of 1 kilometer square. And here we have around 1,200 nodes per sink, or 3,600 in 3 sinks. So thank you very much.
Okay, thank you, Mirza, for the presentation. Any immediate question? We have still time to go for those. Seems to be none at this point. Of course, studies continue. We are and improvement ideas are to be considered. But this is the basic stuff we have been creating. So very good, Mirza. Then I think it's time for Andreas Forzer and Julian Vaihe, for Andreas from Fraunhofer IS and Julian from NXP to present mesh networking for ultra reliable low latency communication. So again, a little bit different area. So stage is yours.
Yeah, so welcome everybody. Thanks for the introduction, Juho. So one aspect of the USWA project deals also about ultra reliable low latency communication systems and how mesh networking can actually be used and exploited for this purpose of achieving a very high reliability and low latency. The results which we together present here are not only from our 2 organizations, Fraunhofer and NXP, it's also from other colleagues participating in this project. So a short overview. So, well, first of all, I will give a short motivation why combining these may be contradicting aspects, mesh communication and low latency communication. Afterwards, I will briefly give a short overview of what exists actually as mesh protocols, with taking into account the URLLC constraints and requirements. And afterwards, we will show some first insights in the ongoing work, advances, approaches, or concepts which we are looking at in order to achieve this. Okay, let's start with the motivation. Well, as I mentioned before, mesh networks they are introduced, developed for military applications in the past, and then are also used and adopted to civil applications. Well known, I think, for everybody. Smart metering is one scenario. Smart home, smart city, also industrial monitoring are typical use cases. And those mesh networks and applications typically have relaxed requirements on the latency. For example, smart metering, if the values from the smart meter, they arrive in seconds or minute range. That's completely fair enough for this application. Also, the reliability, the requirement there is moderate and usually achieved through path diversity. So that means that if one path is somehow defect or cannot be used, then packets are transmitted over another path and routed. On the other side, we have this ultra reliable low latency communication, which means in general, typically it's industrial applications which have very tight constraints on the transmission latency, or specifically real-time constraint. They have hard real-time constraints, and they have a very challenging reliability constraints. For example, in automotive production systems, closed loop control applications, as you can see in the figure at the right side. When controlling a motion, then continuously at an isochronous time range, sensor values need to be read and transmitted to PLC, and then actuator signals are calculated and need to be transmitted to the actuators. So we're talking here about latency values of less than a single-digit millisecond range and error rates of less than 10 to the power of -6. So somehow both domains seem to contradict to each other. But when looking closer to it, actually it can help. So the path diversity can help and also can be used for more novel approaches like cooperative communication schemes, for example. Now I want to dig a bit more in deep in the state of the art. What exists actually already regarding mesh protocols? For sure, as I mentioned before, there are smart home and other applications which use meshed communication systems like Zigbee, etc. So there are a bunch of mesh protocols for wireless sensor networks. But I'm not looking at these right now because they have they are designed for applications with loose latency constraints. So they do not fulfill the objective of your LLC. The first standard, which I want to dig a bit more in deep, is the 802.11s standard, so the meshed extension of the Wi-Fi standard. Some brief information on this. Well, there the multi-hop communication is done by routing on the IP layer level. The nodes continuously scan the topology by transmitting test packets or passive scanning, so observing what they receive. The different clusters of a mesh network, they are separated by frequency, as can be seen in the right figure. So there you see F1, F2, F3, and F4, so different frequencies. And that directly means then if for bridging between two clusters, specific nodes are needed which have multiple transceivers for this. For example, the which you see here, the combining node between F1 and F2 with the transceiver G and H. Some other aspects, well, for the routing and selecting the path of a packet. First of all, in this standard, for each cluster, there need to be defined a root mesh station, which is in the figure to the right, the portal C at the top. And each time if a station wants to communicate with another station, for example, taking the two stations at the bottom, station K and station J, first there need to be established a path to the mesh route station, and this station has the overview of the topology because it continuously transmits test packets and identify by this then the different paths which are possible in the mesh network. And once then this request from station K has reached the mesh routing station C at the top, then it responds with the shortest path between the two communicating stations. So that means that for the real transmission, then not the indirect routing over the portal C is done. Now the direct path is detected and used. But for setting up, it takes a bit of time in order to identify the correct path. When considering this all under the aspect of URLLC communication, well, it needs to be mentioned that as the Wi-Fi standard relies on CSM ACA, medium access control, meaning scanning first the channel with the listen before torque, and only if it's clear and no packet is on the air, then transmitting. This directly means that a tight and strict latency bound cannot be achieved, not with a single transmission. But also later on, we will see also another wireless technology which relies on this. Still, there is the point that with listen before torque mechanisms, we cannot achieve tight latency boundaries. Another standard, well, DEC 2020NR, I mean, it's introduced in the presentations before already. But regarding the perspective of URLLC, some points here, well, the topology, for sure, that's a point-to-point, star topology, possible, it's cluster tree approach here. Other important points are the channel access. So as shown in the presentation before, there can be random access with the listen before torque and so on. But when looking at URLLC, there are also other scheduling approaches which could be used for the channel access, which is then the router-based scheduling, meaning that we're in the cluster, there's a central device, so the cluster head, which defines then and schedules the transmissions. Another important point is that for the network formation, meaning which paths are available, there it relies on that each radio device itself decides. So it's like a self-adaptation mechanism here, an automatic approach. But this can yield a bit to a problem for URLLC communication. If then each device decides individually by himself what path is available and what not. So that's a point where modifications would be needed for URLLC applications. And another standard which I would want to describe here is the echo ring from the company R3 Communication. It bases on the Wi-Fi standard, on the lower layers of the Wi-Fi standard. And it's a kind of cooperative scheme, meaning that if a transmission failed, then a buddy node transmits the retransmission. So by this, it improves the uplink downlink reliability. It can achieve also very low transmission latencies, as low as 2 milliseconds, but this only for very small network sizes. At maximum, this technology supports 20 nodes per channel. And the distance which can it cover, it's well limited to the distance of a single hop. So depending on the Wi-Fi transmission power, it can reach 35 meters or 80 meters. So to sum it up, it's definitely an approach which improves the retransmission reliability. It can achieve also low latencies for very small network sizes. Device-to-device communication is not supported. And besides these three standards which I presented now, we investigated also a bunch of other applications, protocols and technologies, and analyzed them in different methods regarding the reliability, latency, also mesh support, and also if they have some aspects of new innovative communication aspects or methods like cooperative communication or network coding. And the result you see here, and when looking at all the colors, there you see that actually it's only DEC 2020 and R and echoing which comes very close and have already or fulfill already most of the requirements, but still not all the requirements are met or technological approaches are incorporated, which seem to be beneficial for ULLC communication. And by this, then I want to continue with some first insights in the ongoing work in the project, in this part of the project regarding the routing and scheduling. Well, first of all, it needs to be differentiated between the different types of communication. So in mesh networks, we might have intra-cluster communication, meaning that nodes within the cluster, so this circle which you see here, when nodes in between are communicating, that's intra-cluster communication, an uplink, downlink direction. It can also be the device-to-device communication. Then there's an inter-cell intercluster communication, so between neighboring clusters. Their specific node would be needed in order to transmit then the packets in between, or it's fed over the internet. And another important question is if a new node is approaching one of the clusters or multiple clusters, the question is to whom to connect. In general, then also regarding URLLC, different scenarios or types of scenarios need to be distinguished. One scenario would be, since we have the two constraints, its latency and its reliability. So, and if we have constraints regarding to achieve a very low latency, but reliability is relaxed, so that could be, for example, for audio streaming or video streaming. Another type of scenario would be then if we have very tight reliability constraints, but latency is maybe not so a big issue. That's, for example, for logistics, robotics, AGVs, etc. And the most challenging one is if we have really tight latency constraints and reliability constraints, for example, for closed loop control applications in industrial automation, as I have shown in the first slide with the industrial robots. So when looking at the DEC standard, well, it defines different types of packet routing. There can be unicast packets, which would mean that a single packet is transmitted from one sink node to another portable or fixed terminal to another wireless node. There can be multicast packets, which would mean that the single packet from one source could be transmitted to multiple wireless nodes. And there the broadcast packet transmission, which would mean that this single packet from the source is transmitted to all nodes in a cluster. For the routing, for sure, it's important to have some kind of metric to define which path would be the best or how to route a single packet. The DEC standard itself, there's no definition actually for this link cost. Because, I mean, in routing every time, it's about minimizing the link cost for the routing, for the specific routing. And in, so that was in the downlink direction and the uplink direction. It's more simpler in DEC at least. So the problems are mainly the same. So the DEC standard has not defined so far the link costs. So in the project, the colleagues are considering some kind on distance matrix or SNR or power, received power. as matrix, and currently they are looking at packet retransmissions and selecting the path over which then packets are transmitted. Regarding scheduling, some insights. Well, first of all, it's clear that since we consider 3 different application types or scenarios, it heavily impacts also the scheduling approach and the routing. So, for example, for the first scenario type, with this strict latency constraints, or audio-video transmission, for example, there the colleagues are looking here at minimizing the number of hops in order to meet the latency constraints, but having the reliability in mind, but defining their minimum reliability threshold, meaning selecting those paths and links which still fulfill the reliability constraint and threshold, but minimizing the number of hops. The second scenario is about achieving very reliable transmissions, but latency is not so a big issue. There, the colleagues are looking in routing the packet through various multiple hops in order to improve the reliability due to path diversity, and the delays through the additional hops is not of impact, as here the latency constraints are a bit more relaxed. The most challenging, as mentioned before, for sure, is combining both requirements, reliability and latency. So for closed loop control applications. And there the approach is to, first of all, focus on fixed topologies, which is somehow also reasonable, because if I have such closed loop control applications, usually it takes place only in a small area. It's not over large distances in the shop floor of several hundred meters. No, it's about only 1/10 of the meter. So fixed topology seems reasonable. For sure, there can be short-term effects and reflections. So this need to be taken into account, but fixed topology is reasonable in this way. And since we have this low latency constraints, we cannot consider here also this listen before torque scheduling and channel access scheme. So here a router-based scheduling is needed. And then for sure, although the novel technologies, cooperative schemes are considered in this aspect in order to improve the reliability, but keeping then the latency, the transmission latency as low as possible. Okay, and with this, then we would like to conclude our talk. Well, main findings are, first of all, mesh communication is a very interesting option to meet these challenging reliability constraints and latency constraints, since it adds more path diversity, and by this then allows for achieving higher reliability on the transmissions. The other point is that when looking at mesh communication, definitely the application-specific priorities regarding latency and reliability need to be considered in order to adjust accordingly then the routing and scheduling. On the other side, for sure, with mesh communication and multi-hop, the latency can become an issue. So the latency constraints might be not met. Therefore, it automatically limits actually how many multi-hops can be used, depending for sure on the application. Okay, and with this, we want to conclude our presentation. So there are a bunch of references, but yeah, thank you for your interest.
And now we are basically still on time, nicely. So the last presentation will be from Jari Hämäläinen regarding DEC 2020 technology for proof of concept and productive implementation. So basically, where the hardware and software are at the moment. So, okay, Jari will present it from my laptop as he has some challenges to share, but I will put the sharing on and give the laptop to Jari, who is sitting next to me. So, okay, so this is the final presentation and for today, and stage is yours.
Thank you. Very nice to meet all of you in this conference. And my presentation is about the YPAS 5G mesh, and especially from the technology perspective for the DEC 2020 new radio, as well as the proof of concepts and even the product implementation. So that is the focus of this meeting. I will first start with a very quick recap of the standard. How do we see the standard? And then I will go for the use cases and explaining how is the technology actually used in our products, and how do you get access when you are starting to develop your applications on top of our product. So that's the agenda for today. And jumping first for the standard. So new radio plus standard, or DEC 2020 new radio, that is very important from our business perspective, because it is the first non-cellular 5G standard recognized by the IMT 2020. So that is a significant importance among all the different type of IoT technologies and the protocols. And in that standard, important part have been specified from the radio, the physical layer, the media access control, and data link and convergence layer. Also very important for the commercial purposes is the harmonized standard really to verify the capabilities of the product according to requirements. Then I'm jumping to the mesh system, and with this one I'm referring at the NR Plus mesh system, but also our implementation, the YPAS 5G mesh product in the 1.9 gigahertz band. First of all, if we go through the YPAS mesh system and the use cases overall, we have been doing this already earlier in the sub-gigahertz radio area, also in the 2.4 gigahertz radio. But we now utilize the same methodologies on top of the NR Plus standard. And first of all, our customers actually are the hardware product providers. There are various kind of hardware where the mesh radio protocols have been implemented and will be implemented. Also important for the customer is the web user interface, where you can actually monitor and also control the usage of the mesh network for different application purposes. And in our company and the commercial perspective, the focus is on the different type of applications, including the smart metering, smart tracking applications, smart manufacturing, and smart buildings. From the standard perspective, the main benefits we are seeing on the technology is actually listed here. But first of all, we consider this standard to provide amazing performance in unseen cost point. So basically the performance is important and the low cost capability as well. It is important to have an operation on a free license exempt and the global spectrum. This is what differentiates the standards from many different de facto options in the IoT. No SIM card, that is significant benefit for this standard and implementation. We also consider reliability, the uptime of the system, highly important, and in our context, for example, in the smart electricity meters, the service level agreement over the 99.9% is very important and even regulated in some of the application contexts like India. Scalability, scaling up to thousands of equipment in small area or thousands of devices per gateway, and also the network, which is actually extending the range by each node. The superior coverage altogether is also important for the applications, and especially in the most demanding environments. This is a big benefit compared to, for example, to cellular radio. So if you think about the basements, the cellars, or different type of machine rooms having in the difficult locations from the radio perspective, those will be more easily penetrated with the mesh-related functionality. Here is one case example. How do you get started with our product? And in this case, I have been depicting the use case smart electricity metering and the end-to-end customer from the utility. But exactly the same steps are relevant for any application, whether it's in any of the use cases that I mentioned earlier. But first step is for the end customer, like a utility, to build a new solution, to actually think about what they are going to provide. So they are building overall solution. They will select the product to be used in this end-to-end solution. And in this one, the smart metering and the smart metering company will be selecting the right chipset to be used. And that chipset in the DECT NR case is to be with the implementation of bypass 5G mesh, which is pre-integrated in the chipset. Then the smart metering company will be utilizing the bypass software development kit to integrate the bypass 5G mesh into their application. Then they provide the application to the end customer. And at the last phase, end customer is actually running their business like the utility electricity distribution system. If you are wondering how to get started with DECT NR+, then as industrial end customer, you actually should be looking for the right partner for your application, considering the business and technical perspective. And for that one, we as a company have an extensive network or ecosystem of the partners, over 200 companies building different type of applications, and that is the way how this kind of industrial end customer can be choosing the right partner. But if you are a product or solution provider, you can join YPAS partner program in order to get access to our MES product. You can choose the right chipset for your purposes. Then you license the YPAS product, 5G MES in this case, and then get prepared to fulfill the harmonized standard as well as then the product certification like CE marking. But if you are a wireless technology provider, then we recommend you to get familiar with the ETSI standards and actually join the ETSI DECT new radio standardization in order to become a leading wireless technology provider. But let's take an example of the YPAS software product. What is our role in the overall big picture of the mesh networking solutions? As mentioned earlier, there is a device hardware or chipset provider. YPAS is providing a software product, which is the YPAS mesh software product on top of the selected chipset hardware. And on top of that, overall, the companies are building their own applications and their own products. This is considered as one of the nodes in the mesh network, where there are plenty of different type of products connected through the mesh network into the gateway and ultimately to the backend system, providing information to the customer operational and maintenance purposes. And if you wonder how to get started, how to get hands-on with the 5G mesh from YPAS, first of all, we have one SDK which is utilizing all the three radio profiles. As I mentioned earlier, our existing products on the sub-gigahertz range, as well as then on the 2.4 gigahertz BLE area, the mesh system is running on top of those, but now we have also the 5G NR Plus product coming soon. And as a company willing to start hands-on developing your application, you can start by reading the documentation at the developer site about the YPAS mesh. You can download the latest SDK from the GitHub, and then development hardware and software is required. So you start with the existing hardware, your development even today. You can move to the Nordic NRF 91 series of the chipsets as soon as you have been placed an order and when the chipsets are available for you. And then you need to license the required YPAS software binaries, but that's all you need. So that's basically how you access hands-on for the development of the YPAS mesh and also YPAS 5G mesh solution. This is a very busy slide about the functionalities defined in the standard and implemented in our current proof of concept and the product to be introduced. So first of all, in the triangle of the 5G, we are focusing on the massive machine type IoT solutions with the mesh network. From the physical layer and the chipsets perspective, we have been working and pre-integrating on top of the Nordic NRF91 series. There are two chipsets published by the Nordic Semiconductor, the SiP chipsets, which are in our case operating in the 1.9 gigahertz radio band 1 in the NR Plus standard, all the way up to the plus 19 dBm, and with that one, with the different radio conditions, you can achieve the line of sight connection over 5 kilometers, and in the city type of profiles, you can achieve roughly 300 meters range. So basically, depending on the environment, few hundred meters all the way up to few kilometers is the potential range. So we call it the long range profile, which is actually the massive machine type related definition in the standards. From the media access control, we have implemented several functionalities, among them for the transmission, the power control, access related functionalities, and the access control related functionalities. Next hop selection support and the spectrum management functionalities, for example, channel selection and channel change related functionalities, as well as the load balancing with the root cost algorithms. And on the data link functionalities, the key topics, support for the two types of the quality of service and automatic retransmissions, as well as then the next hop routing in the uplink and the downlink. And when we go higher on the convergence layer, segmentation and reassembly functionality for the bigger packages and packet size up to 1,500 bytes. And very important functionality for the mesh network nodes is the firmware update, so the over-the-air protocol to update the firmware when needed. So this is the functionality which we are actually having already available as a beta for the first customers, and also the functionality which we are running every day in our test networks, a bit more than 250 nodes running every day on our testing, and that's kind of the proof of concept we are looking from this research perspective. But if we are wrapping up a little bit about the availability and how to get started and how does the future look like, the summary of the NR Plus availability from our company is our Bypass 5G mesh product. The beta has been available for the first selected customers, but in the first quarter still we are having the general availability for the long range related profile applications in the smart metering, emergency lighting and street lighting as an example, and focusing on the mains powered devices. And we are focusing on the band 1, which is broadly available throughout the Europe, but also Australia, New Zealand, South Africa and India. The focus is really on the non-cellular 5G standard connectivity network for enterprise IoT. A little bit different perspective. You can place your orders for the chipsets coming from Nordic Semiconductor. 91 series of the SIPs with the development kit and the evaluation kit. And after that one, you can enjoy the bypass offering for the selected development applications. But if you think about the work in the USWA, I'm very happy for the results that have been done in the research so far, and also for the standardization. We have a great standard which has been now implemented, and we also look forward for the improvements coming from the USWA program in order to improve the standard for the future and keep the continuous development of the future functionality and better products and services for different IoT customers. And by that, thank you everybody for listening.
Okay, so thanks Jari for the presentation. Any questions to Jari now? Seems to be none at this point. So the clock is 6 minutes to noon Central European time, 6 minutes to 1 in Finland. So we are just in time, nicely. I thank you for all listening this webinar on USWA program. We will continue the project for sure for several let's say years still to go until end of almost end of 25. Let's see if we manage to organize another session we need to think about, but at least from my perspective this was very positive. If you have any questions or comments or improvements, suggestions, and how you feel the presentation and the webinar, let us know. You find my email in the USWA web pages. We are now looking the way to publish this record of the conference. And with these words, it's time to close the session. And I thank all the presenters for your good work. And I hope everybody a nice afternoon in your normal duties. With these words, the session is closed. Thank you.